Hello everyone, this is Dr.S.Lakshmi, Associate Professor in the Department of Electrical and Electronics Engineering, Bharat Institute of Higher Education and Research. In this video, I shall discuss about the introduction of power electronics and some of the basic power semiconductor devices, its VI characteristics and the dynamic characteristics. So we shall discuss topics that comes under unit number 1 of the subject power electronics. So in this unit we have the topics about diode, thyristor, MOSFET, IGBT, its VI characteristics, the firing circuit of the thyristor, voltage and current commutation of the thyristor, and the gate drive circuits for MOSFET and IGBT. So these are the topics which we are going to discuss in this video. So before going into this power semiconductor devices, let me tell you what is power electronics. Power electronics is a subject that concerns with the application of electronic principles into situations that are rated at power levels rather than signal levels. It can also be defined as a subject that deals with apparatus and equipment working on the principle of electronics but rated at power level rather than the signal level. So altogether we can say the power electronics is a combination of two subjects. One is power engineering and the other one is electronics engineering. So power engineering mainly concerns with the generation, transmission and distribution, and the principle is mainly electromagnetic principle, whereas electronics engineering is deals with distortionless production of signals, the transmission and reception of signals at a very low power level. So the advantages of both power engineering and electronics engineering will be combined in this power electronics subject. So dealing with high voltage applications using small rated, miniature devices. So that is the feature of power electronics. So coming into power semiconductor devices, they are devices which are mainly used as switches or rectifiers in power electronic circuits. It is broadly classified into two types. One is two-terminal device, the other one is three-terminal device. And it is also further classified into several categories based upon the type of the device, the number of terminals, type of construction, direction of the current flow, that depends. So broadly, it is classified into two types. One is two-terminal device, the other one is three-terminal device. So under two-terminal devices, we have the diode, Schottky diode, and we have some other types of diodes also. And coming under three-terminal device, we have MOSFET, JFET, IGBT, BJT, and Thyristor. In this, diodes, MOSFET, and JFET comes under majority carrier devices, and IGBT, BJT, and Thyristor comes under minority carrier devices. So coming to a power diode. So what is a diode? So it is a most basic component we use in power electronics. It is basically a switch which has only two terminals. One is anode, other one is cathode. We have only two layers, the P layer and the N layer. So in this power electronics, this diode plays a very, very essential and important role. So it is mainly used in rectifier and many other power electronic circuits. It is mainly used. So it is it can be used as a rectifier and converter circuits. For voltage regulation circuits, flyback, freewheeling diode, it can be used for reverse voltage protection. So we can see the construction of a diode. So we can see we have only two layers, the P layer and the N layer, and N layer is again divided into two segments, the N plus layer and the N minus layer. The P plus layer is called as the anode and the N layer is the cathode. So it is conducting only in forward biased condition. The diode will be in off condition when it is reverse biased. That is, when a negative supply is given to the anode, your diode will be behaving like an open switch. So we can see some of the diodes here. And the construction, coming to the construction, as I said, it has two layers. One is the P layer and the N layer. The N layer is again divided into two different segments, the N plus layer and the N minus layer. The top layer is P plus layer and it is heavily doped. The middle layer is N minus layer, it is lightly doped. And again, coming to N plus layer, it is heavily doped. And the P plus layer act as an anode. The thickness of this layer is about 10 micrometer and the level of doping is 10 per 90 centimeter, per centimeter cube. And this N plus layer acts as a cathode. The thickness of this layer is around 250 to 300 micrometer. The N minus layer acts as a middle layer or a drift layer, and the thickness mainly depends upon the breakdown voltage. I will tell you what is breakdown voltage while we are discussing about the characteristics. And once this layer width is increased, what will happen? Ultimately, the breakdown voltage also will be increased. So that is mainly dependent on this factor. Coming to the working principle, how a diode works. So as I said, it can be biased in two conditions. One is forward bias condition, another one is reverse bias condition. And your power diode will conduct only under forward bias condition. That is when the anode is positive and when the cathode is negative, then only the current flows through it. Otherwise, it will be acting like an open switch. And the range of forwarding voltage drop in this diode is approximately 0.5 to 1.2. Mostly the diodes what we are using in many applications is IN007. For that type of diode, the voltage drop is 0.7 ohms. And in this mode, the diode works as a forward characteristic. It will give a forward characteristic. So the voltage of the cathode is high than the voltage of the anode. Then what happens? The diode will act in the blocking mode, and in this mode, the diode performs its reverse characteristics. So coming to the types of power diode. So broadly, we have three types of power diodes. Depending upon this is mainly depending upon the reverse recovery time as well as the process of manufacturing. It is classified into three types. One is general purpose diodes, fast recovery diodes, and the other one is Schottky diodes. So general purpose diodes, these have very high reverse recovery time, about 25 microseconds. So they are mainly used for low frequency and low speed applications. And fast recovery diodes, these have a very quick recovery act due to its small reverse recovery time. So the reverse recovery time is almost 5 microseconds. So it can be used for high speed and high frequency applications. And Schottky diode, it is a special type of diode. It has an advantage of a forward, or that forward voltage drop is very less than that of a conventional basic general purpose diodes. So in this Schottky diode, the forward voltage drop is very less. So you can turn on the diode with a very small voltage itself. So that is the advantage of this Schottky diode. And it is also, this diode is also classified into different types based upon the depletion region. So it is punch through diodes and non-punch through diodes. So punch through diodes means where the width of the depletion region at the breakdown enters into the N plus layer. And non-punch means the width of the depletion layer at the breakdown does not go through the N adjacent layers. So those are the definitions of punch through diodes and non-punch through diodes. So let us see the VI characteristics of a power diode. So for obtaining the VI characteristics of a power diode, what we do is we have a diode. We are operating the diode in that forward biased condition, and slowly we are going to increase the voltage from 0, and we are going to check the value of current. So when the voltage is 0, that is the voltage between the anode and the cathode is 0, your diode will not turn on immediately. So gradually you have to increase the voltage. So that voltage is called as the forward blocking voltage or the cut-in voltage. So as I said, this is nothing but the only when it reaches this blocking voltage, forward blocking voltage, the diode will be turned on condition, will be turned on. So you can see that until the voltage reaches 0.7 volts, the current remains zero only. So after it reaches 0.7, then only your diode starts conducting. Until then, it is said to be in off condition. Then once it reaches the saturation voltage, the cut-in voltage, then what happens? Your switch will be turned on, then the current gradually increases. So this area, we call it as the forward conduction mode. This is the forward biased condition of the power diode. And what happens during the negative, reverse biased condition? So when the diode is reverse biased, as I said, it is not going to conduct. It is acting like an open switch, but still very small current flows, very small leakage current flows into it till it reaches the saturation voltage. So I'm going to increase the voltage in the negative direction. Negative direction means reverse biased condition. Anode is negative and cathode is positive. So under this condition, what will happen is, even if I'm increasing the voltage, your switch is not going to turn on, but a very small leakage current flows, and once it reaches the saturation voltage, the current rapidly increases in the reverse direction. So this characteristics, we call it as a reverse breakdown characteristics, and under this mode of operation, your diode is off. It is not conducting, it is basically off. Technically, it is said to be in off condition. So that is what has been discussed here, whatever I said. So in forward bias condition, the P is connected to the positive terminal is connected to the anode, and the N side is connected to the cathode. And once it reaches the blocking voltage, the forward blocking voltage or the cut-in voltage, your device starts conducting. And reverse leakage current, this process happens in the reverse biased condition. And coming to the switching characteristics. So what does switching characteristics means? Switching characteristics is nothing but the turn on and turn off characteristics of the particular device. It can also be said as the dynamic characteristics of the device. So now we will see the switching characteristics of a power diode. So before going into it, we will be classifying into two regions. One is the turn on transient, the other one is the turn off transient. So we are going to analyze the various parameters like voltage and current with respect to time. So as time increases, what will be the graph for this voltage and current? So that is what we are going to see in the switching characteristics of the power diode. So we can see the graph here. So we have plotted two characteristics with respect to time. That is the current with respect to time and the voltage with respect to time. So we are going to divide into two segments. One is the turn on characteristics. Another one is the turn off characteristics. So both are with respect to time. So now I'm going to give a positive forward biased condition to the diode, the power diode. So once it reaches the cut-in voltage, what will happen? My current will gradually increase. So you can see that the current gradually increases. Then once it reaches the saturation, once it reaches particular value, it will be stable. It will be constant. So it flows in this way. And now when the forward bias condition, that is when my uh, supply voltage to the anode cathode potential of the diode is removed, what will happen? Gradually my current will reduce. You can see that the curve reduces, but it will not reach zero instantly. Once the voltage across the anode cathode of a diode is removed, it will reach zero, and it will have some energy stored in it to get discharged. So it will take some time. So there will be a negative current flowing across the device, and it will take some time to discharge all the energy stored in both the P and N layer of the power diode. So we can see this is the current curve of a power diode. And coming to the voltage curve, you can see that immediately when the switch is turned on, first there will be a reverse voltage, then it increases, then it will be reaching a particular, I mean it is a leakage voltage. Then once the pulse is removed, that is the supply voltage is removed, the voltage reduces, and again the same as that of the current value, it will not reach zero instantly. The negative voltage flows, and then once it reaches the, then once all the charge carriers are removed, your voltage across the diode will be zero. So till then you will have this energy charged. I mean, it will take some time to get discharged. So till this point, from this point to this point, it is the turn on characteristics, and from this region to this region, you call it as turn off characteristics. Again, in this turn on and turn off, we are going to divide this turn on into two segments, T1 and T2, and turn off we will divide into three segments, T3, T4 and T5. So let us see what is T1, T2, T3, T4 and T5 means. So turn on transient is nothing but it is a transient condition obtained when the diode enters the forward biased state from the reverse biased state. That is from off condition to on condition. So we can see the graph. So the turn on part alone is being shown here. We have the turn on transient regions here. We have split it into two segments. One is T1, other one is T2. So T1 is the charge stored in the depletion region due to reverse biasing is removed, and the diode is now said to be in forward biased condition. It will take some time to get charged, isn't it? Initially, it is taking some time to get charged in the depletion region. So the time taken for the charges to get stored in the depletion region is said to be T1. And coming to T2, the forward biased diode causes the injection of excess carriers into the drift region. So now it will take some time for the excess carriers to penetrate into the drift region, and that time we call it as T2. And coming to the turn off transient. So turn off transient means, what is the meaning? We are removing the voltage for the diode, and your diode is gradually going to turn off. So for turning off, what should happen? The charges which is being stored during the turn on transient has to be removed gradually. So this transient from on to off is called as the reverse recovery characteristics. So it is the transient condition obtained when the diode enters the reverse biased state from the forward biased state, just the opposite of that of the turn on transient. So I have already said we are going to divide into three segments, T1, T2, T3, T4 and T5. So you can see that this is T1, this is T2 and this is T3. Okay, so the time taken for T2 and T3 is nothing but the reverse recovery time, TRR. Okay, this is TRR, and QRR is the charges which has to be removed, the stored charges. So that is reverse recovery charge. So here we have a definition for this reverse recovery time. So due to the minority carriers which remain stored in the PN junction, that is the depletion regions, the time between the zero crossing and the peak reverse current. So you can see that the time taken for the charges to get removed, that is, it is the time taken for the current to reach its negative peak value after it reaches zero. So this is time T2, and then from this point, the current will reduce to 25% of the maximum value. So that is represented as T3, and the sum of T2 and T3 will give you the reverse recovery time. So that's all about the diode. And now coming to the thyristor. So as I said, diode has only two terminals. It is uncontrolled. Either it is on or off. We cannot control during the on time of the diode. We cannot control the switch during the off time of the diode. So we are going to develop the diode from two terminal to three terminal. So next we are going to discuss about the thyristor. So thyristor, otherwise called as silicon control rectifier, SCR. So this SCR is a 4-layer 3-junction semiconductor device. So it is similar to that of a diode, but it has an extra terminal called as the gate terminal. So 3 terminals are anode, cathode and gate. And it is also a unidirectional device. The current flows, the switch is turned on only during forward biased condition, and it is set to be in off condition when it is reverse biased. And as like diode, it is also unidirectional. That is, the current flows only from anode to cathode. No current flows from cathode to anode. So in this thyristor, you have 4 layers. So this is the symbol for a thyristor: anode, cathode. So you can see that the top terminal is the anode, this is the cathode, and this terminal is the gate terminal. And the layers, you can see the construction of a SCR. You have 4 layers: P, N, P, N, and the P layer is connected to the anode, and the next P layer is connected to the gate, and the bottom N layer is connected to the cathode. And we have 3 junctions here: J1, J2 and J3. So here we have, before going into the characteristics and the detailed working operation of a thyristor, we have to see an interesting factor, that is 2 transistor analogy of a thyristor. So we all know what is a transistor. So we all know what is a transistor. So this transistor, 2 transistors connected together in a particular fashion, will give you the thyristor. So the equivalent circuit of 2 transistors shows that the base of PNP transistor T1 is fed by the collector current of NPN transistor T2, and the collector current of T1 feeds the base of the transistor T2. So we have 2 transistors. One is PNP and NPN connected in a particular fashion to give the thyristor. So the conduction of both the transistors depends on each other actually. I will be showing you the circuit shortly. So until one of the base of transistor gets the base current, it will not conduct even if the voltage is present at the anode and cathode. The main difference between the transistor and thyristor is the transistor turns off as the base current is removed. So in a transistor, we have 3 terminals: base, collector and emitter. Once the base current is removed, the transistor will go off immediately. Whereas the thyristor in case of a thyristor, it will not turn off immediately. So this is the structure of a 2 transistor analogy of a thyristor. So this is actually the structure of a thyristor, PN, PN. You can see that this NP layer is divided into 2 segments like this. So this is one PNP transistor and this is another NPN transistor. So these 2 transistors sandwiched together forming a PN-PN layer, that is a thyristor. So we can see this is the structure of PNP transistor. The bottom one is the NPN transistor, and this is the base. Okay, so the base of transistor 1 is connected to the collector of transistor 2, and the base of transistor 2 is connected to the emitter of transistor 1, and the collector of transistor 1 will be the anode of this thyristor, and the base of transistor 2 will be acting as the gate terminal of the thyristor, and the emitter of the transistor T2 will be acting as a cathode of the thyristor. It is exactly the same. So even if one transistor is not working, the other switch will not work. So next, coming to the VI characteristics of the thyristor or a SCR. So here, similar to that of a diode, here also we are going to draw the characteristics under forward biased condition and reverse biased condition. So the basic circuit for obtaining the VI characteristics will be shown now. So this is the circuit diagram for obtaining the VI characteristics of thyristor or a SCR. So you have a variable resistance here, and this is a switch which is connected to a variable resistance again, which is connected to a battery source, and here we have the thyristor and here we have the load. So what we are going to do is we are going to obtain the variation of voltage with respect to current of a thyristor. So here we have the VI characteristics of a SCR. In mode 1, that is in quadrant 1, we get the forward biased characteristics, and in quadrant 3 we have the reverse characteristics, or we call it as the reverse blocking mode, and the mode 1, I mean the quadrant 1 will give you the forward conduction mode, and your SCR, as I said, it conducts only in forward bias condition. So only in this condition, in this mode, your SCR is said to be in on condition. So here, as the voltage increases, so what we are going to do, we are going to vary the voltage and we are going to check the current. So gradually what I am going to do is, I will give some gate current to the gate of an SCR, and gradually I am going to increase the anode cathode voltage of the SCR, and I am going to find out how much current is flowing in the anode. So as the voltage across anode cathode increases, the anode current will be very mildly increased, and once it reaches the VBO is nothing but forward breakover voltage. So once it reaches the value of forward breakover voltage, immediately, even if I'm increasing the value of voltage, the voltage will not increase, and from then the current start increasing rapidly. So only when the SCR reaches the forward breakover voltage, then only your SCR is said to be in on condition. And this curve also can be changed with respect to the gate current. So you can also increase the value of gate current to achieve on condition quickly. That is, if I'm going to increase the gate current, my VBO voltage will be decreased. That is, my SCR can be turned on earlier. So that is the meaning. So this is the forward conduction mode, and similarly this is same as a and diode. That is, when you have given a reverse biased condition, when a reverse negative voltage is given to the anode, what will happen? A very small leakage current flows on the diode, and when it reaches the blocking voltage VBR, what will happen? Then the current will flow in a very rapid way in the negative direction. So this is actually off condition. We get the curve only in the on condition. Practically, with the third quadrant operation is not possible. So the same thing what I have explained you. So now this SCR, turning on off an SCR, triggering nothing but turning on of a SCR. So we cannot do it instantly. So we have some methods for turning on a SCR. So the methods of triggering SCR are forward voltage triggering. That is, forward voltage triggering is nothing but just giving appropriate voltage across the anode cathode. Second one is gate triggering. Next is dV by dt triggering, temperature triggering, and light triggering. So these are some of the methods for triggering the SCR. And now it is the dynamic characteristics. So as I said, transient, we have different names for this dynamic characteristic. You can say it as turn on, turn off characteristics, switching characteristics, dynamic characteristics. So dynamic characteristics of SCR, that it is nothing but the effect of the variation of the voltage and current with respect to time. So what will happen to the voltage and current when the switch is on and when it is off? So the first curve is the gate pulse given to the SCR. So as I said, we have to give appropriate gate signal to the SCR to make it on. So this is VG, the gate pulse to the SCR. So coming to the next curve, we have two curves here. The anode voltage with respect to time and the anode current with respect to time. So as I give the gate pulse, what will happen? My SCR will start to conduct. So once it conducts, what will be the voltage across the anode cathode? It will gradually decrease. So it will be initially maximum. When it is off, the voltage across the device will be high. When it is on, when gate pulse is given, when the switch is on, it will try to reach zero, isn't it? So the voltage will gradually reduce, but of course you will have a small, very small voltage drop. And once it reaches some point, I mean, in the off condition, it will go off. I mean, the charges will be removed. So that is the curve. And next one is the anode current. So when the gate pulse is given, what will happen? It will be moving from off to on. So the anode current will be increasing from minimum to maximum. So this is 90% of the anode current, and this is the maximum value of the anode current. So the same graph is here. You can see it is separated on here. So till this point, first it is 0, then it increases. So this is on condition. And now till this point it is on. At this point, I'm going to remove the gate pulse. That is the meaning. So once I remove the gate pulse, what will happen? The anode current starts decreasing. It will not reach zero instantly. It will have some energy. I mean, it will have some. It will take some time to discharge the energy. Discharges charges. So this is the area for that explains us that there are some charges in it, so which has to be removed for making it off. And this is nothing but the power loss. Power loss is nothing but the product of voltage and current. So coming to MOSFET. So MOSFET, IGBT or voltage control devices. Previously we saw SCR, it is a current control device, and MOSFET is a voltage control device. It comes under FET family. We call it as metal oxide semiconductor field effect transistor. It has 4 terminals, gate, source, I mean it has 3 terminals, gate, source and drain.